Okay, so today we'll talk about a special type of set which is called a group. So let G be a set together with a binary operation that assigns to each ordered pair A, B of elements of G an element in G denoted by AB. We say G is a group under this operation if G satisfies the following three properties. One thing that I want to stress on is the existence of the closure property in this definition. Notice that AB has to be a member of G. This in itself shows that the set G is closed if G is a group. The first property is called associativity. The binary operation defined on the set G should be associative, in that AB times C should be equal to A times BC for all A, B and C in G. The second property is the existence of an identity element, and the third property is the existence for an inverse for each element in G. For our first example, consider the set of integers denoted by Z. Let the binary operation defined on Z be that of usual addition. Now take any three elements from Z and denote them by the characters A, B and C. Then the associativity law holds as described in the fourth bullet point. The identity element is 0, as 0 plus A is equal to A plus 0, which is equal to A for all A in Z. So the identity element exists. Now for all A in Z, there exists minus A in Z such that A minus A is equal to minus A plus A, which is equal to 0. So the inverse of each element in Z also exists in Z. Hence, since all the three properties for a group are satisfied, the set Z of integers forms a group under usual addition. Consider again the set of integers denoted by Z. Now let the binary operation be that of usual multiplication. Take any three arbitrary elements in Z and denote them by the characters A, B and C. Then the associativity law holds as that described in the fourth bullet point. The identity element is 1, as 1 times A is equal to A times 1 is equal to A for any element A in Z. Now assume that for every A in Z there exists an inverse element denoted by D. Then A times D is equal to D times A is equal to 1. This gives D is equal to 1 by A, which is not an integer when A is not equal to 1. Hence, in general, D will not be a member of Z. In general, D will be a member of the set of rational numbers. Hence, Z does not form a group under the operation of usual multiplication.